Hello, this is exercise class 8. So in this exercise class, we have two questions. So why not just start with the first question? So in question 1, so in the system, there is a point dipole embedded at the center of a sphere, which is a linear material and has a radius r, and also the electric constant to be epsilon r, and that dipole point dipole has the dipole moment to be p, and then you are asked to solve the electric potential inside and outside the sphere in this system. So before really start to solve the problem, let's recall what are the effects of a dielectric material under um, in an electric field. So with a dielectric material in the electric field, then there will be some polarization, and it will induce some bound charge in the material. So you also have the bound volume charge which distributes over the material, and also the bound surface charge which distributes over the surface of the material. And these two quantities can be computed using the polarization of that material. So this polarization, if you remember, is that moment per unit volume, and it will be induced if you have an electric field in the system. So here we have a linear material, which means the polarizations and the electric fields are proportional to each other, and their relationship can be quantified using these expressions, which relate them by a linear equations. And the proportionality constant will be just by convention, the epsilon naught, and also the susceptibility, the chi e here. And then the first thing you may want to know is in these linear materials, how and what would be the bound volume charge. And then you can simply apply the relationship between the bound volume charge and the polarization, which is simply the minus gradient, so simply minus the divergence of the polarization. And then you replace the p here with the epsilon naught chi e above, then you should get this expression. And then if you remember what is the Gauss law, so the Gauss law is basically saying the divergence of an electric field would be equal to the charge density over the epsilon naught. But here, keep in mind that the charge density is a total charge density. So it's not just the free charge density or the bound charge density, but it is their total. So here that's why you have the rho F and the rho B here, and plus over the epsilon naught. And then relationship between volume and also their density. So they are proportional to each other and related by this proportionality constant, which is minus chi e over 1 plus chi e. And also there is and the between the polarization and again we just replace p here the expression above and then we get this. So after getting how the bound volume charge is related to the free charge density, then we can just recall in the question we have a point dipole, and the point dipole here, which is the free charge in our system, and therefore there will be some induced charge density due to the presence of this embedded point dipole. And the charge density of the bound charge and the free charge are proportional to each other, and therefore their dipole moment will be also proportional to each other. The point dipole itself and also the induced point dipole, their dipole moment will also be proportional to each other. And then you also use on that sphere. So we can simply use the relationship that we just derived to get the induced dipole moment in that dielectric material. And then effectively, we can regard it as a superposition of two one is a free point dipole and another one is an induced point dipole, and therefore the net dipole moment is just the sum of the dipole moment P and also the induced dipole moment. So which is 1 over 1 plus chi e times the original the bound surface charge, and just sum is a sphere, and therefore the unit normal factor will be simply our head, which is a unit normal factor pointing radially from the center of a sphere. So the dot product between E and N hat will be simply the radial component of this electric field. And again, we can also write the E out here in terms of the potential. So here is a radial component, so which is a minus rho V rho R, and out equals to R minus, the capital R minus. So the reason why it's R minus but not R plus is simply because the polarizations only exist inside the material. So the electric field here will be the electric field inside, just inside the material. So then that's why it's R minus rather than R plus. So at this point, we can just forget about the dielectric, and because we can also think on to reframe the questions into an equivalent system which have a point dipole at the center. But now we have the dipole moment to be P prime, which is the net dipole moment that we just derived. And also there will be some surface charge that created on the surface of that sphere. So here we have boson E equation. And actually you do not really have to start with this boson equation, because you can also so because the potentials is linear. I mean the Maxwell equation is linear, and then you can simply get the potential as a superposition from two contributions. One is from the point dipole, and the another one is from the bound charge on the surface. So for the point dipole contribution, then will be simply equals minus rho over epsilon naught, and for the one from the bound charge, then this one is equal to 0, which is simply solving the Laplace equations, but of course with some with the boundary conditions to get the bound charge density on the surface that we want. So here we can decouple the boson equations into two equations. So the first one is potential contribution from the point dipole, and again we do not really have to solve that because we know how the form of the dipole potentials looks like, which is simply 1/4 pi epsilon naught n times the dot product between the dipole moment and also the unit position factor over r squared. Then we can just simply replace the p prime here with 1/1 plus chi and p. So because the dipole moment is pointing to the positive z axis, and therefore the dot product between them will be cosine theta here. So the one here it would be the contributions from the point dipole. And then the next thing is to solve the Laplace equations. So you can just recall the general solutions of the Laplace equations in the spherical coordinate, and which is simply equation 23. And then the V here would be the total potential that due to both the point dipole and the potential that due to the bound charges. Then we simply add the potential here and the potential here due to the bound charges together. And that's why we have, when it is inside the sphere, we have the double term here and also the term here that is due to the bound charges. So, and then for outside the sphere, we also have this double term, but as you see, the double term can be well absorbed into the expression here. So yeah, so you see it is 1/r squared, then, and also cosine theta is simply the first order Legendre polynomial, and then you can be well fitted into these equations. So just for convenience, we can just get the term here to absorb it into this summations. But it does not mean outside the sphere there's no potential due to the dipole. No, but here we just absorb it into the summation here. So now it will be very straightforward to solve the Laplace equation. So as usual, we impose the boundary conditions. So the first one is to require the potential to be continuous across the boundary. And then the next one would be the difference of the derivative of the potential be equals to the minus surface charge density over epsilon naught. And as we have derived previously, the bound volume charge will be equal to the bound surface charge density will be equal to this expression, and then we simply substitute it into the row B here, and then we will get this expression. So that's the reason why we cannot simply disregard the double term here and just solve the Laplace equation, because the reason why we must have the term here is the the induced bond volume charge, the induced bond surface charge depends on the electric field on the system, and you just cannot separate the electric field between the dipole and also the bond charge. So the bond surface charge here will be due to the total electric field. It will be depends on total electric field in the system, and that's why you can't just ignore the dipole term, but you have to include it into the expression, and then to fit the boundary conditions. So after imposing the first boundary condition by requiring the potential to be continuous across the boundary, then you should be able to derive these two relationships. The one corresponds to L equals to 1, and the another one corresponds to L not equals to 1. And then after imposing the second boundary conditions, you should be able to get these three relations. One is for L equals to 0, and the another one is for L equals to 1, and the last one is for L to be greater than 1. And after combining the relations in equation 28 and in equation 29, then you should be able to show that the A1, there will be only A1 and B1. In all other terms, you just finish. So here is a A1, and then here is a B1. Then we can just simply plug in the coefficient that we just obtained into the general solution. Then you should be able to get the expression here, which is our final answer. But because in the question we are provided that epsilon r rather than chi, so the last step will of course to convert the chi into the epsilon r that is given in the questions, and you can just recall the epsilon r, which is relative permittivity, which is and is simply equals to 1 plus chi, and you can just substitute chi by epsilon r minus 1, then you should be able to get this final answer. And then this is question 2. So the system here will look quite familiar to you, but so I think if you can still remember how to solve the magnetic fields of a infinitely long or maybe just a long straight wire, then here is just a very similar system, except we now that wire, but now we also consider the material property of this wire. So we assume the wire will be made of some linear material with the susceptibility to be chi-m, and now there is a current I that flows down along this long wire, and then you are asked to solve the magnetic field every distance s from the axis, and also to find all the bond currents and also the net bond current flowing down the wires. And yes, and the wire here has a radius a, and also the current is distributed uniformly. So this is the Ampere's law in material, which is line integrals these H fields will be equals to the current, the speed current that encodes in that current loop. And the H field here, by definitions, it is just the magnetic field over mu naught and minus the magnetization. So because in that system we have a circular symmetry, and that's why we will start with the Ampere's law. So so whenever the system exhibits some kind of symmetry, just a spectral, polar symmetry, or etc., then it means that it's possible to draw some surface loop which the magnetic field or the electric field over the surface or along the loop are uniform, and then we will be able to use the Gauss law or the Ampere's law to simplify the calculations. But the law here will be only useful when the system has some symmetry, and luckily we have a symmetry here. Then we can simply use the Ampere's law, and because the system has a circular symmetry, which means the magnetic field will be circumferential and also the magnetizations, and therefore the H field will be also circumferential, which means we can write the H field in terms of the Hs, which only depends on the radial distance from the axis, and it will only has the angular component. Then first, let's consider the regions that is inside the wire. So here the S, the radial distance, to be smaller than the radius R, the radius A. And because the current density is uniform, so inside that inside the current loop that we draw, then the amount of current that we enclose is simply the total current and multiplied by the ratio of the area, by the cross-sectional area of that loop, and also total area, total cross-sectional area of the wire. So again, because along that loop, the H field is uniform, and then we can simply take the H field outside of these integrals, and then the integral will just remain the dl here. So the integral will simply the length of that loop, which is simply 2 pi s. So we have the expression here, and then after rearranging terms, we get the H field to be equals to is over 2 pi a squared. And then let's consider the regions that is outside the wire. So the radial distance S is greater than the radius A. Then similarly the left hand side is just the same. But for the right hand side is always I, because we are now outside the wire, so no matter how large the loop that you draw, you always enclose the current I. And then after rearranging the terms, you will get the H field to be equal to I over 2 pi s. So, but we have not yet finished because you asked to solve the magnetic field. But here we just have the H fields. So if the knowing the property of the material, then we can only obtain the H field. But in the question, we are told that the the wire is a linear material, which means the magnetization is proportional to the H field. Then we can just use these relations and also use definitions of the magnetizations, or I should say the definition of the H field. So actually I mean these E equations. Then you can just manipulate these expressions and substitute away the magnetizations to get a relationship between the magnetic field and the H field. Then you have these expressions. And then, so because the magnetic field is simply equals to mu times H field, then we can simply multiply the H field that we saw in the previous slide by the mu. So when it's inside the wire, then it is simply mu is over 2 pi a squared phi hat. But keep in mind that when it is outside the wire, the mu here it has to be mu now, because now we are outside the wire, which means in a space that there is no material, and there will be no magnetizations, so the Km will be 0 over outside the wire. So that's why the mu here is mu naught instead of mu. So just don't forget about this, and yeah, and you should not just go too fast by something, not applying all the solution by mu. Okay, so the next thing is to find the band volume current and the band surface current in the system. So then we can simply use the fact that the materials is linear, then the magnetization can be easily obtained from the H field, and which is simply multiplying the H field by Km. So here is the magnetizations, and then the band volume current can be found by taking the current of magnetizations. So here we have a cylindrical coordinates, and you can just simply look at the table to check what is the expressions of the curves in the coordinates in the cylindrical coordinate system. Then after looking at the table, then you should see that there's only one non-zero terms, which is simply the derivative here. And after doing this derivative, you should get the band volume current to be equal to this expression. And then the band surface current is a cross product. It's a cross product between the magnetization and the unit normal factor on the surface. So here we have a wire, then or it is basically a cylinder, and therefore the unit volume, the unit normal factor will be simply the S hat, the factor that pointing radially from the axis. So the next thing is to substitute the M that we just found, and then you will see there's a cross product between two unit factor, the phi hat and S hat, and you can just simply use a right-hand rule. So in the cylindrical coordinates, we have three unit factor. The radial unit factor, the S, and also the angular unit factor, the phi hat, and also the last one is factor that pointing to the positive Z direction, the Z hat. And then the cross product between the phi hat and s hat is equal to minus c hat. And that's why we have the bound surface current to be equal to this expression. And then the last thing is to find the net bound current of the system. So basically, it is just there are just two integrals. So the first one is a total current that due to the bound volume current, and the second term is a current that due to that on the surface of the wire. Then you can simply do the integral, and because we have just find that the bound volume current is uniform, and then you can simply multiply the JB here by the cross-sectional area of the current, which is pi a squared. And also similarly, the bound surface current is also uniform along the surface, and then we can simply multiply the K here by the length of the circumference of the cross sections, which is 2 pi a. And then the final result will be simply equal to 0. Okay, so that's it for the exercise class 8. So if you have any questions, just send me an email and ask me to clarify if there's anything confusing to you. So thank you for your attention.